Welcome back, everyone. We'll get started with the last session now. This will have 4 talks, each 15 minutes, 12 plus 3. The first speaker is Prasun Datta, Understanding Systematic 21 centimeter emission.
All right, so let us start and let us try to understand the systematics, shall we? So this is based on mainly 4 papers, which are the last 4 ones. The 4th one is still, I think, in the archive only and been submitted. As you can see, the common thread is calibration requirements for epoch of reionization 21 centimeter observations. And I understand that there are people who are not from the community directly. For them, you can look at the top paper, which is a kind of review which summarizes the difficulties in this field. Now, I guess all of you are quite familiar with the intensity mapping experiments that we have been talking throughout the day, where one try to chase this quantity, which is the H1 power spectrum. And the way you do it is, the idea is the following, that you have the interferometer, which is this block over here, which measures the Fourier transform of the sky, and it can measure in different frequencies. If you correlate the sky at different frequencies, what you get is something called the multi-frequency angular power spectrum, which also you have heard of from Samir and Asif. And it turns out that if I assume the signal to be ergodic, which is that it doesn't have a strong frequency dependence, then it only depends on the separation between these 2 frequencies, and that is directly related to this H1 power spectrum. Now, one can either measure this, which can be actually directly measured, or you can get to it from measuring this. So either is equivalent. The problem is, the first problem that one understands and kind of has mitigated already is that you don't get the sky only. In the visibility that you measure also have the noise. But the nice fact about the noise is that it is not correlated across different baselines at which the visibilities are measured. So one can use the fact that the signal is correlated across the baselines if the baselines are separated a little bit, but the noise is not. So you correlate the visibilities at 2 different baselines that directly measures the multi-frequency angular power spectrum. Modulo something which you can actually measure from your data, so you can actually measure this, measure the maps directly. And then this estimator, because it only talks about this bias which may come from the noise, is actually unbiased because the noise term does not appear here. But of course, it has the uncertainty. The uncertainty comes from mostly thermal noise. But if you go to lower multipoles, obviously, you will have the cosmic variance as well. Now, with this in mind, 20 years back, it was predicted that 100 hours of geometry observation will detect the signal. And we all know that have not happened yet. This summarizes why it have not happened and what is the present status. You have already seen this picture twice from the morning, so I will not go into the detail. We all understand that it is right now limited by systematics. Now, one part that one understood very early is of course the foreground, which again we have talked about very widely from the morning, and it's order of magnitude larger. But the good thing is that it has a different frequency decorrelation as compared to the H1 signal. So one try to use as that. And then you look at different types of the foreground, and over the years, one has figured out how to take care of different types. Like if you have a compact source, which is inside the field of view, you can actually image it and subtract it out. If it's outside the field of view, the tapered graded estimator that Samir and Asif have talked about can take care of it. If it is a diffuse signal like the DGSE, the diffuse galactic synchrotron emission, you have to actually make the power spectrum of the signal and then subtract the power spectrum. But anyway, so there are many different ways, and one kind of figured out, as you have heard many times from the morning, how to take care of the foregrounds. That is a direct effect of the foreground. There is an indirect effect, which is essentially the systematics. And how does that come in, that we will discuss. So what we will try to talk about is what brings in this systematics. Can we estimate it? What is the effect in CLTG? That will be my talk. And just after my talk, Saikat will come in and will tell you the application of this methodologies in 2 cases. One is a UGMRT band 3 observation. Other is a prediction for the SK1 low. So what is the idea? The idea is that the sources has systematics. the systematics comes through the foreground, but through the time and frequency correlated residual gains. And we'll try to understand analytically how these things brings the systematics. Well, so I showed you this equation earlier, only that I have put in the gain, which you know is always there when you do a real observation, which is initially baseline dependent. You can break it down in time dependent and frequency dependent part, and the actual source is the antenna based gains. What does it do? So, well, the gains are there, so you have to calibrate for the gains, but always you can calibrate the gains to a certain accuracy, because your interference has a certain SCFD, so you cannot go beyond a certain accuracy. There is residual gains, and these residual gains, what it does is that ideally you should have got the multi-frequency angular power spectrum measured without a bias with this thermal uncertainty. Now you have an additional bias and an excess uncertainty. These are the things that we have been listening to from the morning. So what you say is that, okay, I have calibrated my instrument to the best accuracy, where I should have got a gain equals to 1, but I have some certain errors. Because of that, this is what happens. The visibility that you get is the H1 on the foreground, and then that 1 plus delta being the small gain error, obviously plus noise. So when you subtract the foreground from the visibility, what remains is not only the H1 signal, but that small delta, which is the gain error times the foreground. Foreground, remember, is much higher than the H1 signal, so delta times foreground can be higher than the H1 signal. That's what you have been seeing. So what we do is that we take very simplified assumptions that the gains are Gaussian random and they're not correlated across different antennas and all. And Shoikat will show that that is quite actually the case. With that, we say that we can characterize the gain with certain standard deviation and certain correlation in either time or frequency. Now with that type of gain, what you do is that you try to use the TG to estimate the power spectrum. And then let us ask the question, how through measurement of TG, now we get a biased estimator, how much can be the bias, how much can be the excess variance. So let me just remind you of the TG, which is that it's a gridded estimator, so it grids the baseline plane and then it looks at a single grid. In that grid, it correlates the visibilities, and then it averages over an annulus region. Now, when you say that in that grids, it correlates visibilities, you assume that the visibilities, the baselines in that grids are all equivalent. That's actually not quite the case because of the following reason. If I think of baselines, they may come from the same antenna pair, but correlate the antenna pairs electric signals are correlated at different times. So they will give you a track like this, and these can be the cartoons of individual measurements. So when you are correlating the visibilities, you may correlate one from here with the other from there itself, or one from there with the other from there, which will give you different types of correlation in the gain. So here what you have done is that listed all different types of correlation pairs that you can get. And then you ask the question that how much of the baselines of a particular pair, of a type of particular pair, compared to the total number of pairs within that grid. Some of these will correlate more, some of these will introduce more gain correlation or gain effect, some of these will not introduce much. And because along this line, as you see that there's the same antenna pair is giving you different visibilities which you may be correlating, it gives you the gain correlation comes in through a factor which looks like this within that baseline grid. The calculations, you may look at the paper, I will not go into the details. But with those, one can, with this all simplifying assumptions and these ideas, one can calculate the bias that we will get in TG and the excess variance. So this is excess variance which adds to the thermal noise. And let me summarize is that what are the different things you have in the bias. So you have the baseline pair fractions coming in here. So this is like two different types of baseline pair fractions here, the other types of baseline pair fractions there. What you may notice here in this entire thing, there is no baseline pair fraction of type 4. The baseline pair fraction of type 4 is when you get one baseline coming from the antenna AB, the other from the antenna CD. So they are all 4 different antennas, so you don't get any correlation. So the correlation across different antennas can be neglected. And then you have time correlation of the gain error, the frequency correlation of the gain error. And then you have the foreground power spectrum sitting over here. It's basically scaling the foreground power spectrum, which is giving you the bias. And in case of the excess variance, you also have the visibility, noise in the visibility. The other thing to note here is that if you look at both the expressions, both B and sigma goes down as a function of number of days of observation. Each day you have observed the same time. This is because we have assumed that the gains are not correlated across days. This probably is what is again we have observed for a long time in the observation. So this is that function chi, how it looks like. As you can see, if you have more time correlation in the gain, the value is usually higher. If less time correlation, the value is lower. That's the message that you can get from here. This is about the baseline pair fraction. One case is UGMRT, one case is SK1 low. What you immediately notice is that the baseline pair of type 4, which is this one, is quite less in case of the UGMRT observations. On the other hand, that is the one which dominates the SK1 low, which is a good sign because then SK1 low, because of its compact baseline densities, will have much less noise compared to the other cases. And obviously, it's analytical. So we validated it against the simulation where we found that the simulations gives you this, which is where you put in all the effects. Different antennas even have different gains. And this is what you recover, which is not exactly right, but a little less, not only a little less. Now, Shaikat will talk to you about the effect that we have seen through this in different GMRT and, as I said, the SK observation. So I just will like to tell you about why it is important. This probably all of you know, but still I want to emphasize. This panel, these two panels are the cases where you don't have any bias. Here you have very less uncertainty. So the true value, and because you don't have any bias, the maxima of the distribution falls in the same place and you say that you have detected the signal. In this case, because the uncertainty is larger, you have not detected the signal. Here, you have a little difference between the true value and the measured value, but because the uncertainty is large enough, you will not be mistakenly saying that you have detected the signal. But the real problem will be here where you have not actually measured the bias and you think that red line is the detection, but what all you detect will be the bias. Okay. And as you will see that this is the case of GMRT, which again, Shaikat will talk to you about. The bias is less than the sigma. This is the case of SK prediction. You see in this region, the bias is actually greater than the standard deviation. So that's the difficult part. So in SK, we are in this region. Well, I will stop there. I will keep this slide where it is telling you that from the observations that you have done and the gain characteristics, you can actually measure the bias and the variance and can assess how good is your observation. Thank you.
Thanks, Prasun. Time for questions. Yeah.
Thanks for a very interesting talk. I understand the gains are only direction independent, right? So you apply
it's all still direction independent.
Yeah,
yes.
so of course, right, in many of the instruments that we're dealing with, we have direction dependent error. So actually the direction independent error is the, right, is some combination of all the gains of the individual tiles or dipoles, right? You form the beam, so then all of those gains are coupled inside a direction independent average gain, and then of course you have the direction dependent ones. Yes. So you haven't analyzed those.
You have not included that yet, but that is in the plan, yes.
Okay, that's in the plan.
So this will not get down to the, still will have some excess.
Okay, okay, thanks.
But at least one can estimate these. And
any further questions?
About SKA, my focus. Oh, fine. Oh, thank you. When you said something about SKA in the last slide, I missed it. I was a bit out of focus. Can you kindly repeat it?
Yeah. Here.
Sorry.
That's all right. So basically, this is a plot of the maps, the multi-frequency angular power spectrum, and the color-coded information is the bias by sigma. Okay, so and you see there is this region where your bias is more than sigma, which is dangerous if you don't estimate the bias somehow. You may mistaken that bias itself as the signal.
Thank you. There was a good talk also overall.
Any further questions? If not, then let's move ahead and thanks our speaker once again.